All right, we are moving on to continue our study of quadratics. The start thinking part says figure A is a large square, figure B is a large square with a smaller square removed, figure C is composed of two large squares with one smaller square added. And what they're looking for you guys to do is discuss, it says write an expression to represent the area of each shaded figure when the side length of the large square is as shown in the first column. So basically, they're trying to get you guys kind of used to the concept of a quadratic and where it would come from and visualizing it and seeing it as an area. So, and they're starting out with you just looking at the square with a number because we know that you guys are comfortable using numbers. So for square A, if it was a 4 by 4, you would say that the area would be 16, which is just 4 by 4, 4 times 4, or 4 squared. The next one would still be that 4 squared, but now a part is missing, a 1 by 1, so it is minus a 1 squared. So you might have called that 16 minus 1, which would be 15. But in an expanded form, it's 4 squared minus 1 squared. And the next one, there's two of those squares that are 4 squared, so 4 squared plus 4 squared, and then you are adding a 1 squared. I did not go over and simplify that, just that you could see the squared aspect of it. Then they change it to saying, well, what about if we didn't know what the side length was and we called it x? Well, now it's x squared, and then the x squared minus 1 squared, and the x squared plus 1 squared, and you may have wanted to combine those to be 2x squared plus 1 squared. And then the next one says, how about when you have the side length being 4x, and that could be 4x squared with parentheses or 16x squared. The other one would be 4x squared minus 1x squared. And once again, that 4x, if you're going to leave it like that, has to be in parentheses because the whole thing is being squared. Or you could have called that 16x squared. And then the next one, each one of those would be 4x in parentheses squared, or 16x squared would have given you 32x squared between the two of them. And then you would have added that 1 squared. And then lastly, they say, what about if the side length was something that was like x plus 3? And in this case, you have x plus 3 squared, and you can see how I adjusted for area of B and C. Now, you guys, I do not believe, have yet learned how to do this thing right here is called a binomial, the x plus 3 squared. You have not learned how to do that. It does not equal x squared plus 9. We're actually going to study this a little bit later on. But basically, they wanted you to be able to see a figure and represent its area by, in some of these cases, with variables and with just numbers. And this actually turns out to be a quadratic, which we'll be studying later. Right now, we're just kind of representing things as quadratics and equations. So this next one here says you have this situation. As you go from step to step, there are more and more of these squares. The first question, or first part says, the number of squares is determined by the step in the sequence. Determine if the situation is best modeled by a linear, quadratic, or exponential function. Hint, make sure that you do it in a way that we have discussed. So we have talked about the second difference. If the second difference is going to be the same, then you know that it's going to be quadratic. So when I made a table and I looked at the second difference, it was 2 and 2. Doesn't really matter what the number is as long as they are the same. So 2 and 2, it is going to be quadratic. Then they wanted you to write an equation. So when you look at this, there's part of the diagram that you can see is growing in a square pattern. Like you end up getting a number that is represented by a perfect square, 1, 4, 9, 16, 25, and so on. So there's part of that that is growing in like a quadratic way, and then there are a few other, in this case, a few other squares that are on there. So what I'm seeing, there's two different parts here. There's the middle that is growing in like a quadratic way. It goes from 1 to 4 to 9 to 16, and I know those are all perfect squares. And then every single one of them has a constant 4 on the ends. So when I do this and I'm trying to figure out what the equation could possibly be, I just focus on the quadratic aspect. I figure out how did step 1 get a 1, and step 2 get a 2, and step 3 get 9, and step 4 get 16, getting that middle box. And I figured out that that was just the step at number n squared. So that gets you the n squared. And then every one of these has just a 4. It's not changing, it's just always 4. And that's why I said plus 4. Now, I was talking to Mrs. Tucker, our math specialist, and I was showing her the second difference, and she actually knew something more than I knew about it. She said, oh, that's, yeah, I knew about that. Not only that, But if you look at the second difference, if you take that number and divide by 2, it tells you what number will be in front of the n squared or the x squared or whatever the thing squared is. So since this is 2, and 2 divided by 2 is 1, then we knew it wasn't going to be 2x squared or 3x squared, or I meant n squared, sorry, 2n squared, 3n squared. It was just going to be 1n squared. So you got your 1n squared, and then you could figure out what is going to go on after that. Lastly, it says how many boxes will there be at the 12th step. And now that we have our nice equation, we could just substitute it in 12, and you get 144 plus 4, which gives you 148. Now, on the second one, it's a little bit weirder because you can't just see like the part that is growing in a quadratic fashion, the part that is making like a square that is just increasing. So it says confirm that the following situation is modeled by a quadratic. You don't want to be trying to come up with a quadratic equation if it's not even quadratic. So what we did here is we set it up as a table. You do your second difference and you get the same number. So it is going to be quadratic. Not only that, but just like Ms. Tucker said, she said that you can get that value and divide by 2, and that tells you the number that goes in front of the n squared. So 2 divided by 2 is 1. So we know it's just going to be 1n squared. Now, part B says redraw the figures so that you can visualize the part that is growing quadratically and then the part that is not part of that. So when I looked at this, I saw for step 1 to get a 1, and step 2 to get a 4, and step 3 to get a 9, and step 4 to get a 16, the square aspect, the quadratic aspect of it, I broke it up. So the first one I had a 1, 4, sorry, the first one I had a 1, then the second one I had a 4, then the third one I had a 9, then the fourth one I had that 16, and then I just put the extra boxes on the bottom so we can kind of analyze how that's growing. So we already see that there is that part that is going to be defined by the n squared. That's how you get your n squared on there. Now the other one, when I'm looking at this, for step 1, you had 2 boxes. For step 2, you had 4 boxes. For step 3, you had 6 boxes. For step 4, you had 8 boxes. So it kind of seemed like you just take the step and multiply by 2. And that's where I got the 2n by. You technically could go over and just make another table with 1 going to 2, 2 going to 4, 3 going to 6, and so on. And then that would be the linear aspect of this quadratic. And you would be able to come up with your equation that way. You would see your rate of change was 2, and then you would see that you didn't have to change, do anything with that. So meaning that 2 times 2 is 4, and 2 times 1 is 2. So that part is already set. So as you can see here, sometimes they're not broken up into like the quadratic aspect and the non-quadratic, like the linear aspect of the equation. So hopefully that made sense. Then it said, how many squares at the 9th steps? You just substitute a 9. 9 squared plus 2 times 9, and that gets you 99. Now, on this next application, you're kind of trying to hunt out the quadratic aspect, the non-quadratic aspect, and try to figure out how you can make an equation. First things first, let's make sure it's actually quadratic before we go crazy trying to make a quadratic equation that doesn't actually exist. So when you do your second difference here, you see that it is a 4. And just like Ms. Tucker said, you could take that number and divide by 2, which gives you a 2. And now you know that it's not just going to be n squared, it's going to be 2n squared, like even if you didn't look at the diagram. Now, personally, what I did was I looked at the diagram and I saw that there were 2 parts that were growing in like the quadratic fashion. For step 1, there were 2 things that were growing that got the 1 by 1 and a 1 by 1. And then step 2, you had 2 things that were 2 by 2. And then the third step, there were 2 things that were growing in a quadratic way. And then the fourth step, there were 2 things that were growing quadratically 4 by 4. So I knew that it was going to have, in this case, 2n squared. I also know it was 2n squared because of what Ms. Tucker told me. Then I'm looking at the rest of it, and I see the bottom has a 1, then it becomes a 2, then it becomes a 3, then it becomes a 4. And that made sense that it was just going to be whatever the step was, you were going to have that number of squares. So that's why I had the n. And then below that, no matter which step you're at, there was always that constant extra 1. So that's why I had the plus 1 on there. I now have my equation, and I can substitute in a 7 in there. And once again, I believe that you could just ignore the quadratic part and then make a table. So you would have 1, 2, 2, 3, 3, 4, and 4, 5. And you could see that it was linear when you checked. The first difference would be the same, and you would see that the rate of change was just 1. That would be that first difference. So you know it would be 1n, and then that wouldn't be enough. You would have to add 1 to it just to make the equation work. And then here, when you substitute in your 7, you get your 36. So now let's move on to the homework. On this, there was a part that was growing quadratically and a part that was not growing quadratically, even though the whole equation will be a quadratic. First things first, let's make sure that it's actually the whole situation as a whole is going to be quadratic. And when you do this, you see the second difference is the same. It is a 2 and a 2. Tucker would say you can divide that by 2 and you get a 1, which means that you know the equation is going to have a 1n squared, not a 2n or a 3n. So you have that. You got your n squared part, and then you see that it goes 3, 6, 9, 12. And what it looked like was every single time you just took the step number and multiplied by 3. And so 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. And that was your equation. So you have that n squared plus 3n, and it says how much at step 8. You just substitute 8 in there, you get 64 plus 24, and that is going to give you your 88. The next one says which of the following represents the pattern, which equation. So what I did was I first saw that at step 1 you got 0, so I just checked were there any that when you substitute in a 1 you didn't get 0, and I saw that A and D you did not get 0, but B and C you did. So then I said, okay, well now I have to go to the next one. Let's substitute in a 2 and make sure you get a 3. And B did make that work, but C did not. When you substituted a 2, you got something different. You got a 2. So I knew that it was B. Number 3, you're supposed to be representing this area, and you're supposed to be generating an equation that represents it. They say the whole entire side length is x. So it's going to be an x by x, which is x squared, and then you have 4 of those squares taken out, and each one has an area of 1, so I just said 4 times 1, and that gets your x squared minus 4. The next one has 2 squares that are both x by x, so that's going to get you 2x squared, and then you're going to have to add 2 of the 2 by 2s, which is 4, and that's how I got my 2x squared plus 8. On the next one on here, you're supposed to be figuring out which parts are growing quadratically, and you can see that you have 3 things for each one of the steps that are growing quadratically, like being a 1 by 1, 2 by 2, 3 by 3, 4 by 4. So that's how I knew it was 3n squared. And then I looked at the next part, and it was for step 1 you had 2, for step 2 you had 4, for step 3 you had 6, for step 4 you had 8. And when you look at that, it's basically the step multiplied by 2, so it's plus 2n. And then you had that floating 1 for every single one of them, so I just added the 1. And that would be the equation. It's not really an equation because you have to, this is technically wrong. I should have written S of n equals or just S equals because it's not an equation yet, but it's supposed to be an equation. S of n equals 3n squared plus 2n plus 1. The next one is saying which graph is going to match the family that it comes from. We know that a quadratic looks like a U, so that means f of x must be the quadratic. We know that we know what exponential looks like. This is exponential growth, so that's going to be g of x. And then k of x is a straight line, so that's going to be linear. And then this next one right here, you're supposed to graph this system of linear inequalities to find out what the solution to the system would be. You've got the x is greater than -3, which is that vertical line for the border, and it's going to be shaded to the right. The other one has a y-intercept of 8, down 2 over 1, down 2 over 1, solid line. And when you try 0, 0, it does work. 0 is less than 8, so you shade in the direction of 0, 0. And the next one you could either get into slope-intercept form, or I just graphed using x and y intercepts, finding out that the x-intercept had to be 6, because I just said 2x, and then I compared it to 12, divided, got x relating to 6. And the other one, you would get -4. You get your 2 dots, solid line, try 0, 0, it does work, so you shade in that direction. So that was just a little bit of extra review. So once again, the majority of this lesson was just making sure that you could look at situations and you could write out equations or expressions to represent them. So number 4, once again, don't forget, if it does say equation, don't forget an equal sign in there in the other side of the equation. Thanks for watching.